LASP, text-to-text optimization for language-aware soft prompting of vision and language models. In this work, we propose a novel text-to-text optimization method for few-shot vision language adaptation that alleviates the overfitting to scene classes problem, preserving and improving upon clips zero-shot accuracy. Thanks to its properties, our method is amendable to training with virtual classes, that is, classes for which no visual samples are present. To further boost the accuracy and alleviate the vision-language misalignment, we also introduce a recalibration mechanism based on normalization, fine-tuning, and class-agnostic corrections. Our approach sets a new state-of-the-art for few-shot vision and language adaptation. Averaged over 11 datasets, our method outperforms prior work by 3% with gains of up to 15% in some instances. Looking one step back, our work builds upon the contrastive image-text pre-training framework introduced by Radford et al., known as CLIP. In their seminal work, the authors show that a two-streamed architecture formed of an image and a text encoder upon large-scale pre-training using image-text data with a contrastive objective that projects the vision and the language components in a joint space, results in a model that exhibits strong few-shot and zero-shot properties. The zero-shot properties of the model can be exploited by processing each class name with the text encoder, constructing a set of class prototypes. The predicted class is then found by selecting the class prototype with the smallest distance to the image features. A popular approach for improving the performance is via hard prompting, where the class names are inserted inside a contextual sentence. To further boost the performance and remove the burden of constructing the prompts from a practitioner, recent work, such as COOP, proposed learning instead a set of continuous vectors called soft prompts, based on a few annotated samples. While notably improving the performance on the classes seen during training, such models tend to lose their in-domain generalization properties, misclassifying similar classes not seen during the few-shot fine-tuning process. As mentioned earlier in the intro, to alleviate these issues, we introduced LASP, a text-to-text optimization framework where we enforce that the learnable prompts should be trained such that they can be correctly classified in the language space against a set of predefined or random textual prompts whose features are constructed using the same text encoder. In other words, the model is forced to correctly classify the learnable prompts into the corresponding handcrafted ones. Intuitively, this works because in CLIP's joint embedding space, similar visual and text examples lie close together, hence making a step in the direction of a given textual prompt prototype should approximate one in the visual domain too. We note that we typically use the textual prompts described in CLIP, but good results can be obtained using randomly constructed sentences too. Moving further, we can observe that as the number of prompts is small, the representation capacity is limited. However, using more within the same sequence leads to overfitting. Hence, we introduce a group-based prompting mechanism where each set of prompts is optimized against a random split of textual prompts, forming multiple sequences instead of one. We note that for inference, we can map back to a single prototype per class, retaining the inference time efficiency. Now, for some downstream tasks, it is possible that there is a data distribution shift between the downstream image dataset and the one used by CLIP during training. Hence, in addition, we will like this aspect to be captured by the downstream adaptation method. In practice, a good balance between adjustment quality and overfitting is striking by layer normalization fine-tuning. We provide more details about this in the paper. Because after layer normalization fine-tuning, the vision and language are not guaranteed to continue to be aligned, we also propose to learn a correction at the output of a text encoder in the form of a learnable offset bias. but aims to realign the two modalities. This term is class agnostic and is a representation of a domain-wide shift instead of an instance or class-specific one. Finally, a direct observation that can be drawn from the text-to-text loss is that in practice, we do not actually have to use only the class names for which you have labeled image data, as the value of a text-to-text loss is independent of the input image. To this end, we propose to learn the prompt using both annotated image text pairs and class names outside of the base set for which we have no images available. We call this setting as training LASP with virtual classes. Our setting combines the best of the both worlds: the guidance from the few annotated images samples and the zero-shot generalizability of language-based training. As we will show shortly, this can further boost the generalization properties of our approach. When evaluated on a suite of 11 datasets, our approach outperforms all prior works significantly, improving upon prior best results by 3% in terms of absolute value. As shown on the left, for some datasets the improvements are higher than 15%, with consistent improvements offered by both LASP and LASP with virtual classes. Interestingly, we also outperform CLIP for in-domain zero-shot recognition, all while retaining and improving upon the excellent zero-shot adaptability of prior methods. Thank you for listening, and I hope to see you by our poster. Feel free to drop an email otherwise. Thank you.